Alison. Okay. So yeah, tonight I'd like to talk a bit about the importance of pattern testing and calibration. So first little photo here is this is our wind tunnel laboratory at the University of Queensland at Gatton. This used to be one of only 3 labs in the world that could test active products. So we've done a lot of characterisation of agricultural sprays here, going back for about 30 odd years, and that's inside the wind tunnel laboratory. I'm just going to skip ahead because I know we're short on time. We first started testing drones in 2017, and it was the XAG, or X-Aircraft as they used to call themselves then, was the first machine we ever tested. And more recently, we've been testing some of the DJI drones. Anyway, some of the issues that we've identified we think need addressing are these listed here. Firstly, people without specialised training can purchase a drone, which is, vastly different to the way that fixed wing and rotary wing pesticide application aircraft work. I mean, those operators have vast amounts of training before they're allowed to, get out there and start spraying. So we think there should be a lot more training done beforehand, before people are allowed to actually purchase a drone and set themselves up as a service provider. Another issue we've identified is there's no agitation of the spray tank with drones. So some herbicides will have on the label that they require constant agitation. So whenever that's mentioned on a label, that really means they're not suitable to be applied by drones, because the drones don't have any agitation. We've noticed that technical issues are very common. There are a lot of sort of glitches in the software, sort of minor breakdowns, and you often do lose quite a lot of your time trying to fix these issues. With the X-Aircraft, you also need an internet connection. And it doesn't sound like a very big deal these days, but even only an hour from campus sometimes, we do have trouble. We've done some work in a vineyard 1 hour from campus, and there's no internet connection there. So that means we have to fly the drone only in manual mode. We can't rely on the RTK base system. And with the X-Aircraft, there's 8 individual items that need to be charged. So you need to be well organised before you head out to the field. The main batteries need recharging quite frequently. So if you don't have power on site, then you do need to take a generator with you. A little issue too is that you can't set the pump pressure for calibration. And also with X-Aircraft, there's usually only one user account that can be operational. So if somebody else within the company is logged on and you go out to the field, you can't then log on because only one user can be operational at any one time. They are dangerous. Drones are dangerous. There have been severe lacerations, and there have also been some fatalities from rotor impact. The other issue is spray drift, of course. I'm going to show a few slides of some of the water problems that we've encountered. The main factors in the spray drift equation is normally your drop size, your release height, and your wind speed and direction. So, of course, with a drone, you're operating 2 or 3 metres above the ground. And wind speed increases exponentially with height, and often some of the earlier drones came with nozzles that only had very sort of a fine droplet size nozzles. So all these factors are sort of working against you when you're sort of trying to focus on spray drift. And recently we've heard from some pilots that there are blind spots with the collision avoidance sensors. The downwash and wake effects, these are very complex and they're not characterised for the many rotor configurations. And the big problem we've identified is swath displacement. That's how the swath moves with the wind. This is not managed at all. The drone itself might be able to maintain a 2 centimetre flight path accuracy, but the swath is not managed, and that needs to be addressed. So you need onboard weather monitoring and algorithms to adjust the flight path. We also need ongoing research and development funded by manufacturers and the chemical companies. Drones, they're classified as an aerial application system, but their speed is more similar to a ground application. And the vortices we've observed are just as bad as you get with fixed and rotary wing platforms. So these are some vortices. These are called wingtip vortices. It's quite asymmetrical on this aircraft. It's to do with the propeller screwing effect. So it's affecting this wing, but not this one. Very well pronounced on this aircraft, your wingtip vortices. So that means your spray is becoming entrained in those vortices, and it's not going directly to the target. The same with this the helicopter over here. You also get vortices underneath helicopters. This is an air tractor, fixed wing aircraft. You can see the vortices there, sort of very pronounced. They're even present on commercial passenger aircraft. And here's a still photo of a DJI drone we tested just a few months ago. We'll have a movie version of this in a couple of seconds. As a matter of fact, now. And you can see the vortices here as the machine's flying, especially if you have the sun behind you early in the morning. You can see them far more clearly.
300 microns, 7 meters a second.
So 300 microns and 7 meters a second of flying speed we just heard.
7, 8.
And then when it stops and turns around, you can even see this vortices from the ground recirculating back up towards the rotors. So I just took out of that. And with the P20, we noticed too that the vortices, I had to draw this with a pen onto the photo. The vortices sometimes draw in the spray back up and deposit it back in front of the drone, as the arrows indicate there. So some mitigation techniques. This helicopter is using a nozzle called an AccuFlow, which produces a VMD of about 1,000 microns, volume median diameter of about 1,000 microns. So with a large droplet, with no vortice effects, droplets only go one way, and that's down. Same with this photo here. In this photo here, this aircraft here, you notice that the boom, it only goes out to about 60 or 70% of the wingspan. And that's another way of ensuring that you don't develop wingtip vortices that entrain your spray. That's just a picture of an AccuFlow nozzle that I referred to a minute ago. These are sort of hollow type needles. And so this one here, for example, 0.016, the diameter of these needles is 0.016 inches, and there's 76 of them on the nozzle. This one is a slightly larger nozzle. It's 0.028 inches, the size of the orifice, and it's got 32 of the needles on the nozzle. These are other mitigation strategies. These are wingtip modifications. These two here were developed at Cranfield College in the UK a couple of decades ago. They're sort of based on the feathers of an eagle. And this one here on the right, you even see these on commercial passenger planes these days. So these wingtip modifications, they take some of the energy from those vortices and then use it to propel the aircraft forward. Here's another simple engineering solution. This is simply a modification beneath the wing, which places the nozzles further below the wing, away from your vortice effects and down into the clean air. So it's just a simple engineering solution. Maybe something like that could be used on drones. You put the nozzles lower down, but beneath the rotors, you might, it might help. So with helicopters, the vortex have been well characterised for many decades now, and the seminal work was done by Parkin back in 1979. However, with a helicopter, you normally only got the one set of blades or rotary wing, and of course with drones there are many different types of configurations, and this is a problem for the regulators because there simply isn't enough research funding to sort of characterise with field work those sort of vortex effects. So we think that perhaps the way forward could be through what's shown here, which is computational fluid dynamics on the right-hand side and particle image velocimetry from the left. This was done by Tang from Nosita in China as well. So just talking about calibrate, why is it important to calibrate? Well, it's important to calibrate so that the correct predetermined amount of material will be uniformly applied over a given area to achieve maximum effect of the target, to ensure the safety of workers and the environment, and to ensure that all equipment is operating properly, to ensure the smooth operation spray project, and prevent overdosing and underdosing of chemicals. And that last one is very important. So this is a simple formula that we use, how to calculate the volume application rate. It's just the rate is simply it's a constant. Uses a constant of 600 times Q. That's the flow rate of all your nozzles over velocity, which is your flying speed in kilometres per hour, times your swath width. And you need to know what your swath width is, and we'll get to that in a minute too. There's another way you can calculate, and that's using this little table here, and Alison might be able to forward this to people if they are interested. The units you use here are slightly different, but it's a similar thing. You need to know the output in litres per minute of all your nozzles. Your speed now is in metres per minute, so watch your units because it will make a big difference. Your swath width, and you just put those numbers into this little formula at the top here, and that gives you your water application rate here. You bring that value down to this box here, water application rate. This is your tank size, so your drain might have a 20 or a 30 litre tank size. The chemical rate, that's what you get from the herbicide or the pesticide label that you're working with. And you just take those numbers now and put them in this little formula here. And this tells you how much chemical you need to add to the tank. So in that example, there's 0.181 litres or 181 mils. So you would add like 6.82 litres of water to your tank plus 181 mils of chemical to bring you up to a total volume of 7 litres. So you don't add 7 litres of water, then add that on top. It's a total volume you come to in the end, which must be 7 litres. So pattern testing, in aerial application, the most important operational parameter is the flight lane, or sometimes called flight line separation. The objective here is to determine the best flight lane separation or swath width for the aircraft. So that is, what's the maximum swath width or flight lane separation that can be flown and which maintains a good T-position pattern with a coefficient of variation below 30%. And it also allows you to check your droplet size spectrum. So for example, if we have a field here and it's 20 metres wide, and we fly 4 times 5 metre swaths, and if each one takes 5 minutes, it'll take us 20 minutes to do that operation. And we might have a droplet size distribution, looks a little bit like that water sensitive paper there. If we fly a 10 metre wide swath, of course, we'll get the job done in half the time. But what's our coverage going to look like? It'd probably be a little bit more patchy than if we flew our 4 sort of flight lines. So we use a value called the coefficient of variation as an objective measurement to determine what is and what is not an acceptable flight lane separation. And we use a value of 30%. So anything above 30% is not acceptable. Anything below 30% is acceptable. So in this example here, you see, come out here, you see this is your COV 30%, this straight line here. If we were to choose flight lane separation of, say, 24 metres, that's well above 30%, that's unacceptable. It only becomes acceptable when it just crosses the line here. So 14 metres is our flight lane separation that we should be operating with that. Anything greater than 14 metres means our deposition will be too patchy and you won't get good efficacy. So the procedure with pattern testing is fairly simple. You just set out some water sensitive cards. The drone should fly into wind. So if the wind is coming from the north, the drone will fly from the south to the north. You should ensure the cards extend a little bit beyond the anticipated swath width. You number your cards and you can place a marker flag in the middle to provide some guidance for the AB line that you're flying. And this photo here is some pattern testing we did on the airstrip at our campus when it operated. You can see these are the water sensitive papers here along this track here. And this flag here provides guidance for the pilot to fly over. That's just a figure of the same sort of setup. When you want to test solid materials, like some pesticide and herbicide products are formulated in granules, you use a setup a bit like this. These traps are made out of sailcloth material, so that when the particles hit these traps, the energy is absorbed and the particles remain within the traps. And there's a little funnel and a jar at the bottom of each of those traps. You just collect that and weigh it. You can use plastic buckets like it, but they don't absorb the energy, so the particles could hit the buckets and then fly back out again. So that sort of an array is far better. It's just an example of a water sensitive paper that's with the droplets on it. One little thing you need to be aware of if you are using water sensitive papers is that the stain that you get on the card is larger than the actual droplet size because of spread factors. Now, there are simple little formulas you can apply to correct for that, but you need to be aware if you are using water sensitive papers, the actual stain size you see isn't the actual droplet size.
3 minutes, Chris.
3 minutes? Okay. As well as using water sensitive papers, you can use some fairly cheap dyes. We use this one here called Brilliant Blue. It's you only use a very small amount, and that's what it looks like when you mix it with some water. You can then use, instead of using water sensitive paper, you use what's called chrome coat. This is considered the gold standard in photographic papers. And that's a cheaper way of doing that. The other thing you can use is pyranine. This is a fluorometric dye. If you're interested in spray drift and you want to quantify your downwind spray drift profiles, then the pyranine is a good choice. Then once you've done your pattern testing, you need to analyse it. Now, we use a program called SWOTKit, which we like. It's very good. You enter all the information into it, and it gives you information about your percentage area, your volume median diameter here, your crops per square centimetre, your coefficient of variation for whatever width sort of you specify. There's another, this is a thing called Swath Gobbler. This was only released to the market a couple of months ago. It's designed for drones. So you fly over this paper strip here, and that's the paper strip after the drone's flying over it with the droplets on it. It's then analysed by this little machine here. And it gives you some statistics on what your pattern's like too. Another one, Stain Analysis, is another program. It's free. I think it's based on ImageJ. Deposit Scan is another program you can use. Nosita, I referred to before, they've developed a similar device to Swath Gobbler, which they have given us one to use. We've only just received that a couple of months ago. We're going to test it out very shortly. Snapcard, little iPhone app. One of our students was involved in developing this. You just take a photo of your water-sensitive paper, and it gives you the data, but you need to ensure that the phone is held at the same height above each card. Okay, how much time, Alison? I just did one of...
Yeah, another 3 minutes is good. Yeah, maybe, I mean, I think it's extremely interesting, and we're not quite sure if we're going to be able to get Professor Young's presentation, but we will record it if we don't get it online today so that everyone can see it. It sort of complements Chris's presentation very well, actually. But Chris, if you give it another 3 minutes or 4 minutes, that would be great.
Okay. Well, I was just going to mention with our X-aircraft machine, we tested the pattern on this. A good place to do it, actually, even with a knapsack or any nozzle at all, is on a concrete slab. So that when it's on the ground, the drone has a swath from the left to the right of 2.1 metres, also from the front to the rear of 2.1 metres. And that's pretty much the pattern you get from a drone. It's not a straight line at all. It is quite up and down. But then again, the last one, that's also a typical pattern from a helicopter. People are quite surprised when they see these patterns. They expect a nice straight line, but no, it's not the case. Anyway, with the SWOTKit program, we found that with the X-aircraft P20, 2.1 metres has a COV of 30.2%. It's just barely acceptable. If you fly with a flight lane separation of 2.4 and 2.7 metres, then your COV is very, very unacceptable. As we found out when we did some testing in a rice crop, these are the water-sensitive papers we placed above the crop. And as you can see, we only got good coverage on 3 out of our 5 papers. And this is when it was 285 micron droplet size, BMD. Flight speed was quite slow, only 1 metres per second. And our flight lane separation was 2.7 metres. It's quite unacceptable. But the cards at ground level actually had a more uniform coverage than the ones above the crop. Then we did it again with the 550, a much larger droplet size now, 550 microns. The same thing, only 3 out of the 5 cards we're getting acceptable coverage. On the ground again, same story again, we're getting better coverage at the ground. And the reason for that, we believe, is because a colleague of ours did some work using bounce and shatter models. And so some of these big droplets, when they hit the ground, they shatter, little satellite droplets form, and they redeposit. So that's why we think we're getting the better coverage at the ground level than we were above the crop. Also, we looked at our deposition in a crosswind, because the manufacturers often tell us that the rotors provide, the downwash from the rotors, assist in the deposition onto the target. Now here, this is the centre line here. These 3 vacant cells here were, these 2 here rather, were directly beneath the drone, and yet with a 10 to 12 kilometre per hour crosswind, you've got no coverage whatsoever. It's all to the left-hand side. Same thing, even at 5 to 6 km/h crosswind, we're getting no two position on the upwind side directly beneath the drone. So the rotors aren't really assisting much with the the downwash from the rotors aren't assisting much at all with our deposition. That's why it's important to pattern test and get a handle on all this sort of stuff. And this last slide just gives us just the formula for the coefficient of variation if you wish to calculate it by hand or to put it into a spreadsheet or something if you don't have a program that will do it for you. Okay, that was the fast version, Alison. So that's about it then. Oh, sorry. Okay, well, that's just a summary, which mainly applies to the P20 that we tested. But, you need to adjust the flight path to allow for wind-induced swath displacement. And the flight control software needs to adjust the number of flight lanes according to the flying height of the aircraft. We say that operators should normally use the coarser spray classification that will maintain efficacy. Applications should be made in a crosswind. So when you pattern test, you do it with a headwind. Applications should be made with a crosswind. Operators should undertake pattern testing to determine the most efficient flight lanes separation for their situation. You don't apply chemicals that require constant agitation. Ensure the aircraft is correctly calibrated, paying particular attention to the pump and flow rates. The risk of spray drift increases with release height, so fly as low as safely as possible. And that's it now.
Fantastic, Chris. Can you keep that slide up just for now? Because I think it's a useful slide as a summary. And I've got some questions, and I know there's some questions in the Q&A. Thank you so much. And just for the audience, I'm sorry it was a bit of a rough start. Unfortunately for Professor Young, the connection's not good, and he's connecting from China, and sometimes that just happens. It's just part of the torture sometimes of running webinars. But I will record Professor Young's presentation separately, and I will add it to the package of materials if we cannot get him to join us later, which we may not be able to do. And it did provide a bit of an introduction for Chris's presentation, which really gave some more detail about those technical aspects. So I hope you found that useful. Chris, I did indeed, and it kind of just, I guess for me, emphasised the importance of really understanding how to optimise drones before getting out there in the field and using it to apply pesticides. So some questions here around, here you're saying that, pattern testing is really important here and looking at the spray drift. How often do you see, in your opinion, this actually being tested and actually operators doing this in the field before going out?
Unfortunately, we don't think it's done quite often enough. There are other techniques people use, which is simply where they use a red dye called rhodamine, and they fly over a piece of string, then they analyse the string, and it just shows peaks and troughs. A lot of people think, well, that's all they're prepared to do because it's very quick. We think it's probably better than doing nothing, but it's a little bit rough and ready. We think you should use water sensitive cards or chrome coat cards with the blue dye, we think, just to double check and see if the swath width separation that the manufacturer tells you that the drone is achieving is really being met, or whether it's way off. And we found ours was way off. But it's the same with calibration. We say people should calibrate before every single spray drop, but we know people don't do that. Sometimes they've got pressures, they've got time pressures against them. I know you've got to remain practical, but you should do it as often as you feasibly can, I think.
Thanks, Chris. Here's quite a few questions coming in now. Due to limited flight time, many of the drone applications or applicators, I guess, or users go for ultra low volume of spraying. I guess, is it ultra low volume of spraying, or maybe low heights? I'm not sure. So
no, it could be ultra low volume. That could be correct. Yeah.
Could be low, Trevor. Okay, ultra low volume of spraying. And what's your comment on this? How does that affect the spraying efficiency and coverage?
Well, I guess people do use ULV spraying with drones because they've only got a fairly small tank. So you've only got a very small volume that you can lift and work with. So it does make sense to use ULV type spraying, or some people call it concentrated spraying. But you still got to be very mindful that you know, of spray drift, because each of those little droplets now has a very, very, very high concentration of active in it. So it might be efficient to operate with that, but you do have to be very mindful of spray drift, that, you know, because you can do just as much, if not more, damage with you know, ULV sprays as you can with your regular sprays.
Yeah. And then, so how much, Benjamin Worthy's got a question around what's your estimate of how much percent of pesticide could be lost from drift? I mean, it depends, of course, on your calibration, but what are some of the numbers?
I'll show you, if I can go back to the slide that I didn't show.
Yep.
So these nozzles here, this orange nozzle is the smallest orifice nozzle. It's called an O1. So an O1 nozzle delivers 0.1 US gallons per minute when it's operated at 40 psi. This green nozzle is an O15. It delivers 0.15 US gallons per minute when operated at 40 psi, and the O2 and the O3, the O4, and so on. And these are the nozzles. These three, these 1, 2, 3, 4 nozzles were the ones that were commonly fitted to the DJI drones a few years ago. And if you look at if you go to the spray catalogues, most of those produce a fine spray. And but getting back to the question, these are your older type nozzles. Now, you know, about 20 years ago, they started using all these coarser nozzles called air induction type nozzles. But before they were available, these were the most commonly used nozzles in broad acre and all sorts of applications. But typically, a nozzle like this can have 40% of the volume can be lost in driftable fines, compared to the newer type nozzles, which might have only maybe 1, 2, or 4% loss in fines. So the losses to fines were huge with these sort of nozzles. Yeah. Absolutely huge. Yeah. I mean, we've done thousands of tests in the wind tunnel with these sort of nozzles, and if anyone wants some real numbers, I can certainly sort of pull some up.
Thanks, Chris. No, that's really interesting. It's quite fascinating. And I've got a couple of other questions. We're going to have to move through fast, so I want to introduce our next speaker soon. But I've got a question here. Thanks for the presentation, Chris. A question on flight lane separation. I guess this has to be optimized for each drone model, question. And secondly, how often do drones need to be calibrated for wind conditions?
Well, yeah, as often, I mean, you should, whenever you make any sort of change, and that change can simply be changing the tank mix partner. So you might add a new adjuvant, or, you know, any sort of change at all, really, you should recalibrate, and maybe not do the pattern testing at every single change, but you know, as often as possible, as you possibly can, you know. And I know that's probably easier said than done for a lot of people when you're under time pressures to get your job done, and sometimes the weather's not that favourable and you've only got a limited window of opportunity to get out there and get the job done. But if you don't pattern test and calibrate, then your job might not get the result that you think you're going to get too.
Okay. Thanks, Chris. I had a question from Ian Gibson in the chat. If you could put that in the Q&A, that would be great, because I think Chris might have a chance to answer that in writing soon. But before we move on to our next speaker, because there's 2 questions there for you, Chris, in the Q&A, I just want to ask, I know that you've been in Cambodia recently and you've been helping with some training there. What kind of training is really useful, do you think, at the moment in some of the countries that you have been working in?
Well, when I went there, because I worked on it was an ACR project Jackie Mitchell ran at the University of Queensland on rice in Cambodia and Laos, and they had a bit of a budget surplus, so they asked me to come on for a year just to look at, you know, drones applying herbicides to rice, and then at the end of that we just went over to Cambodia. We just did 2 one-day sessions on training. But a lot of the training was, we went back to the basics of what we teach to people here in Australia, you know, all about you know, spray classification, you know, the terminology, and all that sort of basic sort of stuff, I guess. Yeah. But also what we've just covered here was your pattern testing and calibration. That was also included. we think that's probably the most important message to get across. And we just did little couple little sort of field sort of tests or examples.
Yeah, perfect. Thanks, Chris. Hey, look, so much information in those slides, and really, really appreciate it. You've got 3 questions in the Q&A. If you could just nip into the Q&A box by just clicking on it, and you could answer some of those questions, that would be fantastic. And everyone, you'll be able to see the answers to those questions as well. Chris, thank you so much, and thank you so much for just stepping in there suddenly and taking over the presentation. That was really appreciated, and we really love having your knowledge shared with the group. And I'm sure there'll be lots of questions, so we might invite you back at another stage to actually go into more of that technical detail and advice. But it does go to show just the kind of training and thinking that we need to be doing to really optimize drones in agricultural context. So thank you so much, Chris. Thank you very much.
Thanks.
The room.
Well, there's some good questions there about how do you handle spraying next to a sensitive area and things like that. We've most of our work over the last 10 years has been on ways of reducing spray drift and drift reduction technologies. So I think it's good that people are sort of switched on to that aspect of chemical applications. Be very, very mindful. Never spray when the wind is spraying towards a sensitive area. We also, I heard you ask someone before, what's the best time for a drone to spray? That's a pretty good question too, because we have been doing a lot of training about not spraying under inversion conditions too over the last few years. Inversions normally develop, well, it depends on which part of the world you're in. I don't know how often they get them in Singapore, but in the early evening until the sun comes up the next morning is the most common times you get surface temperature inversions. About 10 years ago, a lot of people were advocating to spray at night time, but that's not the right time to spray because that's when you get your inversions. Inversions are dangerous because you can't sort of predict which way the spray cloud will move once the inversion breaks down and the wind does start to kick in. A lot of people are often surprised that that you are supposed to spray when you actually do have a wind component. A lot of people think the best time to spray is when there's zero wind, which is exactly incorrect. You do need a small amount of wind to keep dispersing the spray cloud. And as a matter of fact, on some chemical labels in Australia now, they actually specify the wind conditions. You must spray between 3 and 15 kilometres per hour. Happy for any other questions, but
That's fantastic, Chris.